Imagine, just for a second, that you're standing at the entrance of a massive, towering labyrinth.
Oh, I like this analogy.
Yeah, rightly. A maze so complex it stretches way past the horizon. And if you want to reach the center, you basically have three options.
Okay, lay them out for me.
So first, you can put your head down and sprint through the corridors, right? Just mapping every dead end by sheer brute force. Or second, you can somehow cheat gravity, taking a god's eye view to see the whole board at once.
Which is definitely the shortcut.
Exactly. Or the third option, you could become formless, basically seeping into the very walls of the maze itself.
And, I mean, that right there, that is the ultimate universal problem-solving structure. How we choose to navigate that maze tells us, well, pretty much everything about the underlying physics of our reality.
Welcome to this custom-tailored deep dive into the source material. Today, our mission is to explore how to navigate that ultimate maze. We are looking at a really fascinating stack of your sources that synthesize 20th century theoretical physics with, honestly, some bleeding-edge 2026 computational breakthroughs.
Yeah, we're talking giants like Albert Einstein, Nikola Tesla, John von Neumann, and John Archibald Wheeler, all colliding with modern tech.
Right. And we're going to do this through a profound organizing framework that showed up in the sources, which is this biological triad: the cheetah, the eagle, and the octopus.
And, what's crucial to understand is that these aren't just poetic metaphors.
No, not at all. The sources argue these animals are literal biophysical mirrors for classical computing, quantum computing, and artificial intelligence.
What's fascinating here is that for decades, theoretical physics was just completely fractured by two massive debates. On one side, you had Einstein's model of a geometrically curved mathematical spacetime, and that was locked in fierce opposition to Tesla's insistence on this energetic dynamic ether.
Right, the whole empty space versus energetic space debate.
Exactly. And then on the other side, you had von Neumann's really rigid, objective mathematical reality clashing with Wheeler's theory of a participatory, observer-driven universe. Today, we are going to see how modern technology actually proves that, in their own specific ways, they were all absolutely right.
Okay, let's unpack this by starting with the foundation we are currently standing on, like the classical linear progression, the cheetah. Because to understand where computation is going, we kind of have to look at the von Neumann architecture that runs, well, practically every device you own right now.
Yeah, I mean, the phone or computer you are listening to this on, it's a cheetah.
Exactly.
John von Neumann formalized the mathematical foundations of quantum mechanics way back in 1932, but he also gave us the blueprint for the modern CPU. And it relies on a highly centralized processing unit that just executes instructions sequentially.
One after the other.
Right. It's bound entirely by discrete binary states, zeros and ones. It calculates step by step by step.
So it thinks in a straight line, which is why the cheetah is just the perfect biological equivalent here. It's the ultimate terrestrial sprinter, biomechanically engineered for a single axis of forward motion.
Yeah, when the cheetah approaches our maze, it uses a terrestrial brute force algorithm. It sprints down a corridor, hits a dead end, rapidly reverses, logs the error, and sprints down the next one.
Just trial and error at incredible speeds.
Exactly. It solves problems in what computer scientists call polynomial time. But that centralized linear routing comes with a massive structural flaw.
The bottleneck.
Yes, in computing, we call it the von Neumann bottleneck. It's the physical latency, the delay, really, that's caused by constantly routing discrete spikes of data back and forth between the central compute node and the separate memory banks.
So classical computing is like a race car trapped on a two-dimensional track. It can go blisteringly fast, but it can't leave the pavement. And eventually, you can't just keep adding bigger engines. You hit a physical wall, specifically a thermal wall.
That is the inescapable reality of hardware. When you push a classical CPU to its absolute maximum clock speed to brute force an algorithm, the electrical resistance inside those millions of microscopic transistors generates immense heat.
They get literally red hot.
Yeah, and if that silicon hits 95 to 100 degrees Celsius, the system initiates thermal throttling. It deliberately chokes its own performance to prevent the hardware from literally melting into slag.
I love this part of the research because it debunks a wildly persistent scientific myth about the cheetah. For over 50 years, we actually thought cheetahs suffered from biological thermal throttling.
Oh, it is a brilliant example of just completely flawed data collection. So in 1973, there was this famous Harvard University study where they forced captive hand-reared cheetahs to run continuously on laboratory treadmills.
Which already sounds like a terrible setup for a wild animal.
Right, and they found that cats gave up when their core temperature hit 40.5 degrees Celsius. So the scientific consensus just became that wild cheetahs abandon their hunts after about 30 seconds to avoid brain damage from metabolic heat.
Which, if you think about it, makes total sense for a Harvard lab. I mean, if you forced a human to sprint on a treadmill in a stuffy basement, we'd probably tap out and overheat pretty quickly, too.
Yeah, exactly. But then modern field researchers came along and actually surgically implanted thermal sensors and GPS trackers into wild Namibian cheetahs.
The real deal out in the savannah.
Yeah, and they found out the treadmill study was completely upside down. Completely. In the wild, sprinting at over 100 kilometers per hour, a cheetah's body temperature doesn't spike dangerously at all during the run.
It stays totally stable.
It stays perfectly within normal operating parameters, right around 38.4 degrees Celsius. The cheetah does not thermal throttle.
But how? The physics of friction and exertion haven't changed. How does a biological machine dump that much heat that fast?
Through an incredibly specialized anatomical mechanism, the cheetah uses massive nasal passages as a built-in air conditioning system, drawing in huge volumes of air. But more importantly, it uses enlarged frontal sinuses as biological radiators.
Oh, what?
Yeah, blood flowing toward the brain passes through these cooled sinuses, shedding heat instantaneously during the sprint.
But wait, the sources do mention a temperature spike? Just happens after the hunt is over, right?
Yes, the temperature rises about 1.3 degrees after they stop, but it is not from mechanical friction. It's triggered by a massive influx of stress hormones.
Oh, because they're stressed out about losing their food.
Exactly. The cheetah's adrenaline and cortisol spike as it secures its kill and frantically defends it from scavengers like lions or hyenas. So the biological hardware actually solved the thermal dissipation problem that still plagues our semiconductor engineers.
That is wild. But here's the catch. Even with perfect cooling, the cheetah is still trapped in the maze. It's bound by physical, two-dimensional walls. And this is exactly how your sources connect classical compute to Einstein's macroscopic universe.
Einstein's general relativity.
Right. Einstein gave us general relativity, a mathematically elegant, continuous, four-dimensional space-time fabric. It is beautiful, but it is strictly bound by local realism, absolute speed limits, and geometric determinism.
It is a rigid stage. Just like the cheetah's musculoskeletal structure, Einstein's classical universe doesn't allow you to simply bypass the walls of reality. If the maze gets too complex, running faster in a straight line just isn't going to save you.
Right. If the walls are unbreakable, you can't push through them. You have to cheat gravity. You basically have to change your dimensionality.
Which is where we reject the terrestrial two-dimensional maze entirely. We move to the eagle and the leap into quantum computing.
Taken to the skies.
Exactly. Instead of running sequentially, the eagle achieves a God's eye view. By utilizing quantum superposition and entanglement, it observes the entire vast, multi-dimensional probability space concurrently.
So it doesn't test individual paths one by one.
No, it uses quantum interference to instantly collapse all probabilities and pinpoint the single optimal vector.
And just like the cheetah, the sources show us that the eagle isn't just a metaphor here. Birds are literally utilizing quantum hardware in their own biology. I have to admit, when I first read about avian quantum magnetoreception, it sounded like pure science fiction.
I mean, I don't blame you. It's one of the most astonishing discoveries in modern biology. Inside the retina of an eagle, and many migratory birds actually, there is a highly specialized light-sensitive protein called cryptochrome 4, or CRY4.
And what does it do?
Well, the mechanism here is pure quantum mechanics. When a photon of ambient light strikes this protein, it acts like a microscopic cue ball. It excites an electron, knocking it over to a neighboring part of the molecule.
Okay, creating a pair.
Yes. This creates what we call a radical pair to electrons that are now quantumly entangled.
Meaning whatever happens to one instantly affects the other, even if they are separated. But, and this is the crazy part, this is happening inside a living, warm eyeball.
Precisely. Because their quantum states are permanently linked, they become exquisitely sensitive. The incredibly weak magnetic field of the Earth subtly alters the spin dynamics of these electrons, which changes how quickly they chemically recombine.
So it changes a chemical signal in the eye.
Right. This quantum interference creates a specific chemical output that the bird's visual system overlays on its physical site. The bird doesn't just feel the magnetic north, it literally sees the magnetic gradients as visual patterns.
Which is mind-blowing because human engineers at companies like IBM or Google are struggling with massive, energy-intensive cryogenic cooling systems, getting down to near absolute zero just to keep their synthetic habits from falling apart. And this bird is sustaining quantum states at warm biological temperatures while flying through the sky.
It proves that nature has already mastered high-dimensional quantum processing, and human science is rapidly trying to catch up to this complexity. Just look at the breakthrough from the University of the Witwatersrand in early 2026.
Oh, the photon study.
Yeah.
For a long time, we thought of a photon as a relatively simple thing, right? Like a wave going up and down or a basic particle.
Right, very basic. But they unlocked a hidden 48-dimensional world inside a single photon.
Wait, how does a particle of light even have 48 dimensions?
By manipulating something called orbital angular momentum, or OAM. Imagine a beam of light not just traveling in a straight line, but twisting like a tornado or a spiraling corkscrew as it moves forward.
Okay, I can picture that.
By altering the shape of that twist, researchers discovered over 17,000 distinct topological signatures hidden within entangled quantum light.
17,001 photon.
Yeah. A single photon isn't just a pixel of light anymore. It's carrying profound structural complexity. It's a vast new multidimensional alphabet for quantum information processing.
And to process that alphabet, we are seeing major shifts in how quantum computers are actually built. In March 2026, Google Quantum AI announced they are expanding into a dual modality strategy. They actually recruited Dr. Adam Kaufman to lead a new effort in Boulder focusing on neutral atom quantum computing. I know superconducting qubits are the standard, so why the pivot?
It's all about how you scale to match the high-dimensional reality of the universe. Historically, Google focused on those superconducting qubits, and those are incredibly fast operating in microseconds, and they allow for deep, complex circuits, but they scale in the dimension of time.
What happens when you try to scale them physically?
They hit physical, energetic barriers when you try to pack millions of them tightly together on a chip. Neutral atoms, however, operate entirely differently.
How so?
They use highly focused lasers, called optical tweezers, to trap individual uncharged atoms in a vacuum. They are slower per cycle, sure, but they scale beautifully in space.
Because they aren't wired down.
Exactly. Because they aren't hardwired into a silicon grid, you can form flexible dynamic arrays of 10,000 atoms with any-to-any connectivity. You literally dynamically rearrange the physical qubits to match the geometry of the problem you are solving.
Okay, hold on. If light and space possess this incredible dense complexity, and if we were trapping atoms in a vacuum using lasers, doesn't that mean Nikola Tesla was right about the ether? I was taught that the famous Michelson-Morley experiment explicitly disproved the idea that space is filled with an energetic medium. I thought Tesla's ether was debunked pseudoscience.
Well, it disproved the rigid, mechanical 19th century version of the ether, the idea of a stiff physical wind blowing through space. But the broader concept, Tesla was actually profoundly correct.
Really?
Yes, Tesla rejected Einstein's empty geometric space, insisting the universe was permeated by an invisible, dynamic, space-filling substance. And what's not widely taught is that Einstein himself conceded in 1920 that a purely empty geometrical spacetime was physically unthinkable.
He actually went back on it.
He did. He stated that space without an ether would mean no propagation of light and no standard of space and time. Today, modern quantum field theory has resurrected Tesla's ether under mathematically rigorous nomenclature.
Which is what?
We call it the quantum vacuum and the Higgs field. Space is not empty. It is a seething, dynamic sea of virtual particles popping in and out of existence, full of zero-point energy. Tesla's energetic ocean and Einstein's elegantly curved geometry actually synthesize perfectly into modern physics.
This is wild. So we've mastered the hardware of the ground, the classical cheetah. We've mastered the hardware of the air, the multidimensional quantum eagle. But what if the ultimate trick isn't flying over the maze? What if it's becoming the water that floods it? It's time to talk about artificial intelligence and our third biological mirror, the octopus.
Now, this is where it gets really strange. If the cheetah is centralized and linear, the octopus is radically decentralized and formless. Of the 500 million neurons in a common octopus, only about a third are in its central brain.
And the rest.
Over 300 million neurons are distributed throughout its 8 arms.
Meaning each arm is basically a semi-autonomous expert. It can touch, taste, and make complex micro-decisions completely on its own, without waiting for permission from the brain.
And this maps flawlessly onto the most advanced AI architectures today, specifically the mixture of experts or MOE model. In a MOE large language model, the system doesn't activate its entire massive neural network for every single prompt.
Because that would be computationally ruinous, right?
Exactly. Instead, a central routing network, like the octopus's brain, analyzes the prompt and dynamically directs the data to specialized submodels or experts trained to handle that specific task, whether it's writing code or translating French.
And the physical adaptability of the octopus is just as crazy. They have no bones, they can pour themselves through a hole the size of a coin, and they adapt at the molecular level. Your sources detail how cephalopods react to sudden drops in ocean temperature. Most animals have to wait for generations of DNA evolution to adapt to cold, but the octopus uses something called A to I RNA editing.
Yes, and the mechanism is brilliant. RNA carries the instructions from DNA to build proteins. The octopus literally swaps out a specific chemical letter in its RNA on the fly.
It just edits its own code.
Yeah. This editing process subtly changes the physical shape of the resulting proteins in their nervous system. They rewrite the structural weights of their own biology in a matter of hours to ensure their neurons keep firing perfectly in freezing water.
Which is the exact biological equivalent of a machine learning technique called low-rank adaptation, or LoRA. AI engineers use LoRA to continuously fine-tune an AI model's internal parameters for novel tasks without having to retrain the entire foundational base model from scratch.
Right, it's real-time parameter updating in response to environmental data. The octopus isn't just reacting to its environment, it is dynamically shifting its physical reality based on the information it receives. Which perfectly bridges us to the second great physics debate. John von Neumann's rigid objective mathematics versus John Archibald Wheeler's participatory universe.
I want to make sure I fully understand Wheeler's theory because it sounds pretty intense.
Wheeler was a true visionary. In 1977, he argued that the cosmos is not a static objective stage that exists independently of us. He proposed the maxim it from bit,
It from bit, what does that mean exactly?
meaning every physical object, the it, derives its existence entirely from binary yes or no information, the bits. The universe essentially waits for an observer to ask a question, and that observation forces a wave function collapse from infinite probability into a definite reality.
Here's where it gets really interesting. Generative AI mathematically proves Wheeler's theory. The architecture of a large language model is basically a miniature participatory cosmos. Before you type anything into ChatGPT on your phone, the AI's latent space exists in a state of quantum superposition.
It contains the mathematical potential for every sentence ever conceived by humanity, but it doesn't know anything definitively.
It requires the observer. When you type a prompt, you are acting as the quantum measurement. The AI must break down your continuous human reality into computable fragments through a process called tokenization.
Which is the literal realization of it from bit.
Exactly. And your prompt triggers a mathematical engine called the softmax function.
Now, softmax is...
Let me stop you there because softmax can sound a bit dry. I like to think of the softmax function like a roulette wheel.
Okay, I can see that.
The AI has thousands of possible next words, all spinning around, each with a different probability score of being the right choice. Softmax is the process that forces the ball to drop into a single slot. It forces a collapse into a single observable sequence.
That is a perfect analogy, and the temperature setting of the AI acts as the control for the randomness of that roulette wheel during the collapse. A high temperature means the ball might bounce into a less likely slot, giving you a more creative answer.
So when I type a prompt, I'm not searching a pre-written database. I am literally collapsing a mathematical universe into a brand new reality. And the AI's self-attention mechanism even mirrors Wheeler's theory of retrocausality, the idea that the present can rewrite the past.
Yes. In a transformer model, if the AI generates the word bank, that word exists in the superposition of meanings. It could be a financial institution or a river's edge.
It doesn't know yet.
Right. It isn't until the AI generates the word water later in the sequence that the attention mechanism reaches backward in time, performing a quantum erasure to rewrite the dimensional weight of that past word to support the emerging present.
What absolutely blows my mind is how the AI's identity fundamentally alters the physics of its universe.
If we connect this to the bigger picture, Wheeler believed the universe responds first to the identity of the observer. In AI, this is the system prompt, the hidden instructions that tell the AI who it is supposed to be.
The invisible rules.
Yeah, when you assign an identity to an AI, it triggers system prompt-induced linguistic transmutation, or SPLIT. It mathematically suppresses the probability weights of out-of-character responses and elevates domain-specific ones. By telling the AI you are a helpful pirate, you literally shift the physics of the model's reality to make pirate vocabulary mathematically inevitable.
So it's all connected. The geometry of Einstein, the energy of Tesla, the math of von Neumann, and the participatory observation of Wheeler. But here is the harsh reality. To make this fluid, participatory AI octopus actually function at scale, we run into a very terrestrial physical wall, the KV cache bottleneck.
Right. The brutal reality of serving long-context AI is that every single token you input must be stored as a complex, high-dimensional vector in a high-speed working memory.
The key value cache.
Yes. This key value cache swells rapidly the longer your conversation gets, completely devouring the GPU's video RAM. The wall isn't compute power anymore, it's memory bandwidth.
It's basically the AI equivalent of the Cheetah's von Neumann bottleneck. The memory gets choked, so how do we fix it? By synthesizing everything we've learned into software, specifically Google's TurboQuant, released in March 2026.
TurboQuant is a marvel of applied geometry. It aggressively compresses this KV cache memory down to just 3 bits per value. That yields a 6x reduction in memory consumption and up to an 8x increase in inference speed on NVIDIA H100 GPUs with absolutely zero loss in accuracy.
Okay, my skeptical alarm is ringing. How is zero accuracy loss even possible when you are shrinking the data that aggressively?
By using Einstein and Tesla-like spatial transformations, standard compression methods map data onto a Cartesian grid, think of plotting points on an XYZ graph.
The standard high school math graph.
Right. But storing the exact grid coordinates for every single data block requires massive memory overhead. TurboQuant uses a first stage called polar quant. It mathematically rotates the data into polar coordinates.
Meaning instead of using a grid, it uses a compass. It represents the data entirely as a radius for magnitude and angles for direction.
Precisely. And because angles are mathematically predictable, they exist on a continuous loop, you don't need to store all that extra overhead instruction data. You just capture the relational essence, the direction of the vector.
But there has to be some margin of error when you compress that much, right? I mean, nothing is perfect.
There is a minuscule residual error, which is where the second stage comes in. The QJL transform. It acts as a 1-bit error checker.
Just 1 bit.
It's just 1 bit. Think of it as a simple parity flag. It uses a single bit of data just to flag if a coordinate has mathematically strayed too far from its expected angle, ensuring the transformer's attention mechanism remains flawlessly precise. It is the ultimate synthesis. Using the rigorous linear algebra of von Neumann to manipulate spatial geometries like Einstein, all to sustain the high-dimensional participatory fluid intelligence described by Wheeler.
So what does this all mean? When you, the listener, pull out your phone today to use an AI or look up a complex problem, why does this matter? Well, this isn't just about massive tech companies saving money on faster chatbots. By fundamentally changing the economics of computation at the hardware level, we are successfully mapping the multidimensional physics of reality into usable everyday software. We are learning how to build tools that genuinely mirror the universe.
We started with the grounded, sequential speed of the Cheetah, trapped by physical walls but optimized for blistering linear execution. We elevated to the Eagle, utilizing quantum superposition to see the entire probability space at once. And finally, we found the Octopus, the formless, participatory intelligence of AI that adapts its very structure to permeate the maze.
Navigating the challenges of your own life requires a synergy of all three. You need the rigid structure and sequential logic of classical thinking to execute your daily tasks. You need the elevated perspective of multidimensional thinking to see the big picture and spot the hidden connections. And you need the fluid adaptability of the network to squeeze through the unpredictable gaps when the environment gets cold.
And this raises an important question to leave you with. John Archibald Wheeler posited that the universe is a mirror. It responds first to the identity of the observer. In artificial intelligence, this is the system prompt. We act as the observer, collapsing the high-dimensional probability field of the latent space with our prompts. If our generative AI is truly a high-dimensional mirror of our collective probability field, and it only responds to the identity we project into it, well, what does the current state of our AI reveal about the unwritten system prompt of humanity itself?
What identity are we projecting into the void? The maze is out there waiting for your next move.